Hello there, 8th graders. This is Mrs. Minowitz, and I'm here to go through how to do the calculations looking at absolute age of rocks. So the first thing that we need to know is when we're using these, doing these calculations, the formula that we need. So A is equal to P times 0.5 to the T power. But you also need to understand what those things represent, so when you are doing the questions, you'll know what to put where. So P is the starting amount. What did we start with? A is the amount remaining of our original element that has not been changed yet. And then T stands for the number of half-lives. So think of time, but it's not just the time that you are given, it is the time based on the number of half-lives. So when we are looking at using half-lives, we need to understand how this works. So for every half-life, you lose half of what you had. So when you look at number 2, when it says number of years after formation, it's broken apart actually by half-life. So if you look here, we're looking at cobalt-60, and cobalt-60 here has a half-life of 5.27 years. Okay, 5.27. So when we go and start looking at this, 5.27 here really means one half-life. So in one half-life, we have lost half of our 100%, or it's not really lost it, but it's decayed. So we'd say we'd have 50% of the original cobalt-60 remaining. After 2 half-lives, we would now have half of that half of that 50%. So that would be 25%. And we continue dividing by 2 as we move down the chart. So this would be 3 half-lives. We have 12.5%. This would be 4 half-lives. And that would then be 6.25%. So we're just losing half of what we had. We keep dividing by 2. Now we're going to use our equation here to calculate some different things and how much we would have remaining. So if you had a 20-gram sample of carbon-14, how much carbon-14 would remain in 28,650 years? Well, let's write our equation up there. A is equal to P times 0.5 to the T power. It tells you start with 20 grams, so that's P is 20 grams. And we're trying to figure out how much would remain, so we're solving for A. We also need to figure out T, so remember T is the number of half-lives. To figure out the number of half-lives, you take the time that you are given, 28,650 years, whatever time you are given, and you're to divide it by how long a half-life is. So if you go back to your chart, you look at carbon-14, you find the half-life of 5,730 years. So I'm going to divide the time given by the half-life. And when I take this and I divide it in the calculator, I get 5. And this tells me that T is equal to 5. So I'm going to go through and put that in the equation. A, the amount remaining, that's what I'm solving for, is equal to what we started with, which they tell us is 20, times 0.5, okay, to the T power, which is the 5th power. Now remember, when you are putting this into the calculator, you want to make sure you do the exponent first. So 0.5 to the 5th power. And then you're going to multiply that by 20. And if you have done this correctly and put this in your calculator correctly, you get A equals 0.625 grams. That is your answer. This is what would be remaining after 28,560 years. All right. Same type of thing for question number 4. If you had a 40-gram sample of americium-241, how much would remain after 1,082 and a half years? Same setup. You write the equation. A is equal to P times 0.5 to the T power. It tells you what you started with, that's P. It tells you you started with 40. We need to figure out T, just like we did in the last question. They give us a time here, 1,082.5 years. I need to divide that by how long a half-life is. So if I go back to the chart, I see americium-241 has a half-life of 433 years. So I say I'm going to divide this by 433. Now this one, when we divide, we don't get a whole number, which is fine. We would say 2.5. It's gone through 2.5 half-lives. So we know that T is now equal to 2.5. So we can put it in the equation. A, that's what we're solving for, is equal to what we started with, 40 times 0.5 to the 2.5 power. Now again, remember you do the exponent first when you put this into the calculator, so you'll do 0.5 to the 2.5 power. and then you'll multiply that answer by 40. You want to make sure you don't round your answer first. Put it all in, like keep it, but don't round it and then re-put it back in. When you do this, you're going to get A is equal to 7.07 grams. This would be your answer. So we would be left with that much remaining. So for these types of questions, remember, the hardest part a lot of times for students is getting T. Remember, take the time I give you, divide it by how long a half-life is. That will equal T. For question number 5, we have the same type of thing, except we have to do an additional step here. So it says, suppose that you had a 100-gram sample of iodine 131. How much iodine 131 would remain after 100 hours? Now, that normally we'd be like, hey, I can go through, I can set up my question, I got my equation, I know that. I know that I start with 100. Now I need to figure out T. The problem is when you go to the half-life and you look up the half-life of iodine 131, it is in days. It's in 8.07 days. So what you need to do first is convert your 100 hours into days. So I'm going to take 100 hours, I'm going to divide by 24 because there's 24 hours in a day, and I get 4.17 days. Then, so this is like the time you were given. Now I need to take my 4.17 and divide it by how long a half-life is, which, if you look at the chart, is 8.07 days. So I will divide that there, and when I do, I get 0.516. So T this time is a decimal again, 0.516. So I'm going to go through and put this into my equation. A is equal to 100 times 0.5 to the 0.516 power. Remember, do your exponent first, then multiply by 100. When you do that, you should get that A is 69.9 grams. Same idea for the next one. If you had a 75-gram sample of polonium-215, how much would remain in 0.018 seconds? Really short period of time, but still same type of question. So we write our equation. I write how much we started with, 75. I'm trying to figure out T, so remember to figure out the time. I take what I'm given, and I divide it by the half-life. And if you go back and look at the half-life on here, it is a very, very short period of time, 0.0018 seconds. And when you take and you divide those two numbers into your calculator, you get 10. So you now know that the number of half-lives is 10, so T is equal to 10. And then we can go through, plug this in, and solve or answer our question. So you get A is equal to 75 times 0.5 to the 10th power. You're going to get a smaller number for this because 10 half-lives is a lot. So when you do that, you're going to get A is equal to 0.073 grams. That's how much you would have. For number 7, what happens to chlorine-36 over time? So chlorine-36, if we look at our chart, is something that is radioactive. So we would say that over time, it is going to decay. And this parentheses over here tells you what it actually decays into. So if you look here, chlorine-36, we actually have another element there, argon. So our best answer here would say it decays into argon. Number 8 is a little bit more tricky here because it's asking you something quite different. It says, suppose that you find a fossil that is 11,460 years old. This fossil contains 5 grams of carbon-14. How many grams of carbon-14 did this fossil originally contain? It might be helpful to make a T-chart instead of using the equation for this question. There are a couple different ways you can answer this. You can use the equation. And there's nothing wrong with that. It's just you have to realize that it is giving you A and asking you to solve for P. So you can go through, set up your equation. A is equal to P times 0.5 to the T power. And it says it contains 5 grams of carbon. How much did it originally contain? So you would have to recognize that A was equal to 5. And you'll have to then solve for P. So you'll still figure out T. just like what you did before. So you take the time given, 11,460, divided by the half-life. If you look that up, it's 5,730. You get 2, so t is 2. You would then need to plug those in and solve for p. So that is one way to do it. Sometimes people are like, whoa, that's way too much. There's another way you can do this by making what's called the t-chart. So if you put on here years old and amount of carbon-14, you can set this up and work your way backwards. So if you're saying, hey, I know that this fossil is 11,460 years old, okay, and I know that at that point in time it had 5 grams of carbon-14. What I can now do is say, like, I can go backwards and calculate this. So this here, okay, if I go back a half-life, so if I subtract 5,730, because that's how long a half-life is, I took the 11,460 and subtracted 5,730, I got 5,730. I know that's one half-life. In one half-life, I would lose half of what I had. So I know to go backwards, I would need to double what was there. Because if you think about it, hey, at this point in time, it's a half-life, I'm going to lose half of it. You can work their way backwards as well. You can also go, okay, now if I take my 5,730 and subtract another half-life, I'm back to 0 years, which is present day. I would need to then double what I had. Okay. So you're always going times 2. You need to double what you had and get 20. So either way you do this, you should get an answer of 20 as you go through this. If you're still having trouble with this, make sure you come in and talk to me. Otherwise, best of luck with this.